order or second order. So now let's get back to where we left off from our previous lecture, and that is the Arrhenius equation. All right, so I want to begin. So this is new material, Gina. One major theme that I was harping on is this idea of temperature, okay? So what are some of the things we learned in this class that are quoted at a specific temperature? One of them, if you remember, is vapor pressure. Is it not so? Vapor pressure is quoted at a specific temperature. Vapor pressure is quoted at a specific temperature. I did not really emphasize this, but viscosity. Remember viscosity? It's one of the properties of the liquids, one of the three main properties of liquids. Viscosity is quoted at a specific temperature. And finally, what is quoted at a specific temperature is this theme, which is a theme of this chapter, rate constant K. So rate constant lowercase k, if you remember, is quoted at a specific temperature. So, and then we also mentioned, is it not so, that if you increase the temperature, what will happen to rate constant K? It will usually go up, right? So this whole chapter is dealing with rates, quickness, speed, velocity, and as you increase the temperature, let's say the reaction, you run it at, instead of 25 degrees, you run it at 50 degrees, we would expect the rate constant for that reaction at that higher temperature to also go up, okay? Rate constant is sort of a constant for each reaction that tells us how fast the reaction is proceeding. So we're talking about the Arrhenius equation, okay? Arrhenius. So we have a rate constant K1 at T1, temperature 1. We have a rate constant K2 at temperature T2. You remember this equation? I know it's very, must have been a couple of days ago, but we have a vapor pressure at T1, and then we had a vapor pressure at T2. Okay, this is called the Clausius-Clapeyron equation. Okay, we did this in class. Okay, and actually I believe it's on your test, your written test. Okay, that's the relationship between Vp at T1, Vp at T2, and we have a delta H vaporization. Okay, so question on the exam related to that. Here we have K1 at T2 and a K2 rate constant. I'm sorry, here we have a K1 at temperature T1. We have a K2 rate constant at temperature T2. And what sort of bridges the gap is the activation energy. We talked about the activation energy in our previous lecture. Remember, that's the hump. The activation energy is the hump, the barrier that you have to undergo to descend, go downhill into products. Okay, so what's this equation? This equation is called the Arrhenius equation. Okay, shown here. Yes, page 16. Okay, Arrhenius equation. And here is the Arrhenius equation. Okay. Thank you. I'll give this to you on the exam, so you do not have to memorize it. Does this look like anything to you guys? It looks just like... Yes, exactly. Okay, it looks just like the vapor equation. It looks just like this equation here. Okay. So here we have a common theme that's going on.
Sorry, I have to drop my brother off. He's gonna be late.
So here we have natural log of K1 or a natural log of K2 equals the activation energy over R, 1 over T2 minus 1 over. So a couple of things here. R is going to be this value. I'll give R to you on the exam. It's going to be 8.314 joules over a mole Kelvin. Okay, that is the value of R. So R is the gas constant. I'll give that to you on the exam. And like before, okay, like you mentioned before, if we're given 3 of these K1, T1, T2, we can solve for K2. If we're given T1, T2, and K1, we can solve for K2. So if we're given 3 out of the 4, we can solve for the other one. So here's the equation here. It looks just like, these two equations look just like one another. Okay. Right, so next up is we will do a problem involving this. Okay, so you can see there's many different versions of this equation. So this is the version that we will use for our problem. And let's go ahead and do that on page 7 of our notes. All right, this is a practice problem that involves the Arrhenius equation. All right, so the first order rate constant for this reaction of methyl chloride with water produces methanol and hydrochloric acid. And the rate constant for this reaction, K1, is 3.32 times 10 to the minus 10 inverse seconds. Okay, so this is K1, this is T1. Calculate the rate constant. We'll call that rate constant K2 at temperature T2, 40 degrees C. And they give you the activation energy of 116 kilojoules per mole. So let me rewrite the equation one more time for you guys. Okay. This is the Arrhenius equation. Natural log of rate constant K1 over rate constant K2 is going to equal to EA over R times 1 over T2 minus 1 over T1. So the first thing I would do when doing this problem is I would convert this activation energy to joules per mole. Okay, so step 1 would be convert EA, activation energy, to joules per mole. And I would convert these temperatures to Kelvin. First step I would do, let's go ahead and do that. 116 kilojoules per mole times the conversion is 1 kilojoule has 1,000 joules. Okay, that's the relationship. The kJ, kilojoules, cancels out with the kJ, and we're left with 116,000 joules per mole. Okay, that will be our EA. Right, and let's convert our temperature. We have T1 temperature at 25 degrees C. If we add 273, correct, we'll get it in Kelvin. And that is 298 Kelvin. Let's do that for T2. 40 degrees C plus 273. And on my calculator, what is that, 313 Kelvin? Now we can plug everything into our equations. All right? So natural log, I have K1 here as 3.32 times 10 to the minus 1. 10 to the minus 10, excuse me. So that will be our K1 here. Let's plug everything in. We don't need to put units inside the natural log. Okay, mathematically, you're not allowed to put units inside the natural log. Yeah, add them at the end, correct. Yeah. K2 is what we're trying to solve for, is it not? Okay. That's going to equal to EA. So let's put EA here as 116,000 joules over mole times R. I'll give you R, so don't memorize it. Bless you. Bless you again.
Thank you.
So R is 8.314 joules over a mole Kelvin. 8.314 joules. Okay, over a mole Kelvin. Okay, I'm going to move it up to the top. Joules over a mole Kelvin gets flipped up to the numerator. Times 1 over T2. 1 over T2 is 1 over 313 Kelvin, minus 1 over T1, which is minus 1 over 298 Kelvin. All right, so we have everything here. It's joules over mole Kelvin. And so it's joules over mole Kelvin. Yeah, okay, here, joules over mole Kelvin. So let me backtrack a little bit. EA here is, how about I answer it this way? Let me just not put the numbers in. Let me just put the units in. The units of activation energy are joules over mole. What are the units of R? So, of course, I'll give you these numbers and the units. It's joules over mole Kelvin. Okay? So remember now, whatever's in the denominator, so if you have a fraction in the denominator, this denominator moves back up. So this is equal to joules over mole, joules. This mole over Kelvin goes up to mole Kelvin. By the way, this mole, this joule, and this joule all cancel each other out at the end, because the joule was in the denominator of this fraction. This is a fraction within a fraction. The joule stays...
Oh, I see. The joule next to the mole.
Yes. Yeah, this is not chemistry. This is algebra, math.
That's wrong.
Yeah, but I'm trying to cancel out the units. Yeah, that's the thing. So like I said before, the just joules, this joules cancel, this mole cancel. If you calculate this with the units, the kelvins actually cancel as well. If the units cancellation troubles you, what I would do is, I don't like doing this personally because I think this is more thorough. You can do all the numbers, the math, and then put the units at the end, provided that you know you put in the right units. But I like carrying the units, canceling the units, make sure they make sense. All right. Our goal here now is to solve for K2. How will we do that? All right, this is a calculator exercise, so you can follow along with me. Okay. All right, I'm going to solve for this on the right-hand side first. Okay, so let's do that. So it's going to be 1 divided by 313K minus, everyone see this, minus parentheses, 1 divided by 298. Okay, so I did this 1 over 313 minus 1 over 298, and I got this value, right? Times 116,000. Okay. 116,000 equals that number. Divide that by 8.314, and we get that number here. So this is the number I'm going to write down. So all of this is going to equal to minus 2.244. Okay, 0.244. All of that must equal to the natural log of... No, it doesn't mean anything, because what we need to do is solve for K2. So how will we solve for K2? Do you remember how we solved for K2 in the other problem? Okay, we take the, not the natural log, but the inverse natural log. Okay, so we're going to take the inverse natural log of both sides of the equation. Remember this? Inverse natural log of both sides. Okay, what is the inverse natural log? Shift ln e. Very good. Okay, if you take the shift ln e, if you take the shift ln, it becomes e to the power of natural log of 3.32 times 10 to the minus 10 divided by K2. You just take the inverse natural log on your calculator times e to the power of minus 2.244. Okay, what is e to the power of natural log of something? It's that something. So e to the natural log of x is just x. Right? Remember this from the first problem we did? So e to the power of natural log of this thing is just this thing. Okay. So 3.32 times 10 to the minus 10 divided by K2. Now what is e to the power of minus 2.244? That is something we'll put on our calculator. So you guys know how to do this? I don't know if you can see this, but it's going to be shift natural log. That's e to the power of minus 2.244. Okay, we'll close those parentheses. And this is our answer, 0.1060. Okay, are we getting that? E to the power of natural log of this thing is just that thing. E to the power of this number is this 0.0160. Maybe I'll put in another number here, 3. Okay. And now I'll solve for K2 here. So for solving for K2, I'll put the K2 this way, and I'll put the 0.10603 down here. So again, this is math, not chemistry. 3.3 times 10 to the minus 10 divided by 0.10603 is equal to K2, and this should be my final answer. 3.13 times 10 to the minus 9. And don't forget to put back in the units. And the units are, what are the units of the rate constant? Inverse seconds. So you want to put in the units. Seconds to the power of minus 1. No, this is the right answer. You can write it this way. Yeah, that's the right answer. Yep, you're right. Correct. Very good. Yeah, these two are the same, Chidera. So that is the answer. Okay, so this is not on test 1, but it will be on test 2. If you can, yeah, it's the same thing that we did before. Does this kind of ring a bell? Okay. Okay. You can come talk to me if you need more help on the math side of things. But yeah, that's what it is. So T1 here at 25 degrees, our rate constant is 3.32 times 10 to the minus 10. Okay, the units of that are seconds to the minus 1. At T2, 40 degrees, our rate constant is 3.13 times 10 to the minus 9. So you see that it's gone up. It went from 10 to the minus 10 to 10 to the minus 9, so it's increased. We increased the temperature, and K1 has increased from 10 to the minus 10 to 10 to the minus 9. That's what I was trying to say at the beginning of class. As you increase temperature T, you increase rate constant K.
So it's like, it's direct.
Correct, direct. Okay. A lot of things, as I mentioned at the beginning, a lot of things are quoted at a specific temperature, with vapor pressure, viscosity, and this rate constant, lowercase k. So that's the Arrhenius equation. And
What's like the best way to I think my problem is identifying which equation to use. Is it just like?
well, you don't have to memorize the equation, So I'll give you that equation, and I'll give you the constant. So it's just a matter of utilizing the equation. Now, if you're given like a MCAT or one of these chemistry exams you take for your whatever, licensing or whatever these big formal exams, they'll give you a sheet of equations, and then you have to select which one is the right one. But for my exam, I'll give you the equation. Okay, you can make sure you know how to use it.
You do it next to the problem, or do you just give us like a sheet of equations?
I'll put it by the problem. All right, so a question like this will appear on your exam, not the one this week, but the one next week. Okay, because we're almost 3 weeks and a couple of days before we finish the class. All right, lastly on chapter 13, we're going to talk about catalysts. And do you know what a catalyst is? Maybe what is the definition of catalyst in your life? Enzymes are catalysts, most definitely. Yep, there's about 50 to 100,000 enzymes in your cell. So enzymes are everywhere. So yeah, what do enzymes do in this chapter, in this context? Okay, the main theme of this chapter is speed, right? Speed, velocity. So it increases the speed of the reaction, right? So that's what a catalyst will do. So how will a catalyst increase the speed of the reaction? It lowers the activation energy, okay? So here is an uncatalyzed reaction. Remember, EA is that hump. Once you overcome the hump, everything is downhill. And enzyme will lower that hump. Okay, it lowers the activation energy. So what does a catalyst due to the rate constant K, just like temperature increases rate constant lowercase k. Yes, very good. The catalyst will increase rate constant lowercase k. Okay. And before I end this chapter, so two main things here that you should know for the exam or when you take your, bigger exams, more important exams. A catalyst is typically associated with lowering the activation energy and increasing the rate constant lowercase k. Okay? And you can see in the reaction coordinate diagram, it lowers the activation energy. So here's something from maybe life experience or something. If you take potato, just potato, and slice it and dice it, okay? Potato has an enzyme, okay? Chidera mentioned an enzyme as catalysts. There's an enzyme in potato called catalase. So here you can buy this potato from Walmart or whatever grocery store. You can also buy H2O2 from Walmart or whatever your favorite store is. And the H2O2 actually decomposes to H2O and oxygen. Okay, decomposes. That happens very, very, very slowly. That's why when you go to Walmart to buy hydrogen peroxide, you're buying hydrogen peroxide, you're not buying water and O2 because this reaction is so slow. Okay? But if you take this same bottle of hydrogen peroxide, 3% or 6% from the Walmart, and you add some diced potato, diced potato, you'll immediately start seeing bubbles. Okay, what are those bubbles? Okay, those are oxygen bubbles. Okay, so what happens is that potato is saturated. It's tons and tons of the enzyme catalase, and the enzyme will make this reaction go super fast.
Is that
Yeah,
like water?
you need to get the enzyme out. So what we do is kind of like dice it or try to crush it with a mortar and pestle, or maybe even blend it. Yes. So if you blend this or put it in a mortar and pestle, you're kind of breaking open the potato cells. Add the H2O2 and you should see oxygen bubbles. Yeah.
Is this safe to do at home? 'Cause I want to put potato in hydrogen peroxide. Is that safe to do at home?
You can do it at home. Yes.
She said, is it safe?
I just
It's
want
going
to
to
try it.
explode.
You said bubbles, so I'm just being cautious.
Yeah, it's safe to do at home.
Experiments going on.
So that is a catalyst. Okay? And that is the end of chapter 13.